goes up. Saving rate goes up. Saving rate goes up. Little s. So guys, can you help me? I am going to just ask you like previous chapters. I ask you to draw a graph and then explain what happens. From graph point of view, anyone? Anyone? Actually, this is easier, honestly, if you ask me. What happens to the graph? If saving rate goes up, what happens? No. There is only one curve. Yep, yes.
The SFKT goes
Yeah,
up.
yeah, exactly. You see this one, so-called, make sure you know the name. So this is representing over investment / saving per capita equity. Exactly as he said, you see, production function remains the same, f of k, but s f of k, as he said, shifts up, okay? So, get it here? So therefore, statistical equilibrium goes where? Human statistical equilibrium is determined by intersection. So your O is statistical equilibrium is determined this. This intersection goes here. Okay, did you see that? So your long run very long run equilibrium goes from point O to point O prime. Did you see that? So actually here we have a little bit problem. Okay, what's the problem? You see, Yomer won Nobel Prize because by this model he contributed a lot to economic theory because his model was first growth model. Okay, so first of all, first discovery that he made was that, which was empirical. He realized that U.S. economy, representation of all economies, have been growing continuously. He was the first person discovering that U.S. economy has been growing 2% per year on average for more than a century, 120 years. U.S. economy on average, annual average, 2%. But you know, this model doesn't explain that. Why? Because remember, when economy was at point O, what is growth rate of per worker output? You see, economy stays there, is that right? Economy stays there forever. So, when economy gets to steady-state equilibrium based on this model, it looks like economy doesn't grow anymore. And this is not consistent with something that Mr. Solow himself discovered. Okay? Actually, you guys don't remember when I was your age, okay? There was a very big opinion saying in order to have continuous growth rate, we need to have higher saving. Okay, people were always promoting more saving, more investment. Okay, actually these days even we have people like that. Okay, but as it turns out, this is not enough. Why? Because if saving rate goes up, yes, you see, per worker output goes up permanently. Sorry, per worker capital, per worker output go up permanently. However, growth rate goes back to zero. You see, when you go from O, growth rate of economy becomes positive for a while, taking economy from O to O prime, and then growth rate goes back to zero. And you know that human is greedy. We want continuous growth rate of economies. Okay? So, and it looks like it has been that way in the past. And of course, we want that more in future. But this model doesn't show that. This model doesn't show that. Yes, levels go up permanently, but all growth rate go back to zero again. Okay? So, another thing for final exam that many people get stuck in final exam. In final exam, in this part, sometimes I ask people to draw timeline of variables. For for example, I ask you to draw the timeline of output per worker. What does that mean, timeline? It means output per worker, output over time. Okay? Okay? So it's a very popular, people who miss everything, classes, everything. Popular question in final exam, they ask me, what do you mean by what? This change, you see, remember, growth rate of output per worker was 0, steady state. Eventually, it goes back to 0 growth rate. So growth rate becomes temporarily positive, take economy from this level to this level, and then growth rate dies, goes back to 0. And that is something that Mr. Solo's own model couldn't explain continuous growth rate of real life economies. Okay, but we are going to fix that next chapter. Chapter 9 is just to fix that. Okay, another, as a matter of fact here, can you see it here? This is empirical study, which shows economies which have higher saving rate, they have higher per worker, per capita, of course, per capita income. Okay, so, but my point here is we want growth rate. Okay, actually, when I was your age, life was completely different. Another thing was, many people said, population growth rate must go down. You guys possibly heard about that. What? I have seen that. So in those days, countries had, almost all countries had very tight population policies to reduce population growth rate. Policies that these days, those countries are sorry about that. In fact, about my country, I was part of that plan, okay? I fight a lot to reduce population growth rate back in my country, okay? So I am guilty, okay? But you know, in those days, it looked very bad. Such that, I remember, the United Nations giving money to countries, including my country, so we got money to reduce what? Promoting policies to reduce inflation rate. Sorry, to population growth rate. Why? Because they thought this is a problem. So that can help growth if population is smaller. You know that these days we have, you heard about Elon Musk? He's talking about population collapse. So many, if something going on now, if it goes on by the end of century, many countries are going to have half of population today. Like South Korea, Japan, China, European countries, even my own country that I fought to reduce population growth rate, now fertility rate is dangerously small. You know that. Fertility rate must be 2.1 to just replace population. But even in my country, which used to have one of the highest fertility rate, now people are telling me is 1.4, 1.3, which means what? By the end of century, population of country would be half. That is scary. And by the way, the population, by the way, would be mostly old people. So young people, labor force, don't exist. Okay, so you see, okay, that represents those days. But even those policies turn out to be not very good. Oh, okay, I was supposed to ask you guys. So did you see that? So okay, I gave it away. So you know that this is slope. This slope is n plus delta. Is that right? So when population growth rate goes down, so you have rotation. Is that right? So rotation of depreciation rate, depreciation line, rotation. So as you can see, it looks like it helps. It helps, you see? It helps, but not permanently. Okay? So even if it is useful, because in this model, it doesn't consider very, very, very long term, okay? So, but again, there is another problem. I mean, the same problem. Yes, levels go up permanently, but growth rates go up to zero. You see here, when you go from O, growth rates become positive shortly, taking you from O to O prime. At O prime, all growth rates go back to zero again. I am talking about per worker variables. So if you have a timeline, so the timeline is like this. Like this here. It helps growth rate of growth we want, I repeat. So it helps growth rate of economy just temporarily. So another problem. So these are policies. How about shock? Guys? Okay, so I am not going to make that mistake. So suppose, God forbid, we had an earthquake, okay? Suppose nobody dies, but 1/3 of capital stock just is destroyed. Capital stock overnight becomes 2/3. And nothing else, no other change. Anyone? What happens? Any suggestion? You remember one thing, we talked about that? Shift versus move along. So it works here too, okay? It works continuously. So what variables can cause move along? Remember, variable on vertical axis, variable on horizontal axis, they cause only what? Move along. So other variables, remember, other variables N, S, shift, we did that. But here, capital stock goes down. And capital stock is not a shifter. That is not a shifter. It causes what? Just move along. Okay, so it means, look at here. So you see, your economy just overnight jumps from here to here. Is that right? Because capital stock is changing, nothing else. So there is no shift. Okay? But then what happens? At this level of capital stock, remember last week? Inflow of capital is larger than outflow of capital. So what happens? So you are going to have gradual adjustment back to full long run statistical equilibrium. Do you see that? No shift. So there is a jump and then adjusting back to old equilibrium. Remember point O, we call point O as stable statistical equilibrium. If stable means if you are out of that, you go back to that point. Okay? Okay, here we go. So timeline. How does per worker output timeline look like that? I mean, over time, yes? So, can you see that? Per worker output was at its steady equilibrium. All of a sudden, capital stock falls, output falls, but then you have gradual adjustment back to old steady equilibrium. That's it. Okay, so your shocks, policies, so the same thing that we did last time. Sorry?
Was the earthquake example, why are we having growth rate of per worker output and per worker capital increase instead of decrease?
So why per worker output decreases? Because, yes? This one?
Yeah.
Okay. I just said that. You see, right after earthquake, you are here. Is that right? So this much capital stock is destroyed. So output goes down right away. Is that right? So right after earthquake, I am here. But at this point, this is what we discussed last week. At this point, capital inflow, this is capital inflow, is larger than capital outflow. Capital inflow is more than capital outflow. You have a tank of water, so it means capital gradually goes up. So there is a shock and then gradual adjustment. Does it make sense now?
Yeah.
Yeah. So I told you, generally in this model, point O is stable steady state equilibrium. So it means if you are anywhere to the left, you gradually, you go to point O. If you are anywhere to the right, be careful. The same thing is correct for the right. If you are anywhere to the right of point O, so you gradually go back to point O. You over? Stable steady state. Okay. Actually, this Solo model helped a lot. That is another huge discovery of Mr. Solo. You possibly heard about, when I was your age, everybody was talking about engine of growth. What causes growth? Okay? So during my time, people said investment. Remember? Saving, investment. Even today people mention that. Even today people talk about that. Okay? But Mr. Solo, in fact, if you ask me, I believe this is the biggest of his discovery. Okay? So, the question here is, so if investment is engine of growth, so it means more investment, more saving is always good. Is that right? But is that right, really? So is always more investment, more saving, more investment a good thing? So as you can see here, no, that is not necessarily a good thing. So that's why we need to find optimal saving, optimal investment. Can you see it here? Optimal saving, optimal investment. Now let's investigate and find what is optimal saving, what optimal investment is. So I am going to approach this in three ways. Number one, just by trial and error. Number two, graphical. We need to find graphical optimal investment saving. And then we are going to use math. Is that right? All three. Let's do the trial and error. Okay? What do I mean by trial and error? Remember? Optimal investment. Investment is equal to what? Saving. But saving itself is what? Saving rate times income. Is that right? So if you want to find optimal investment, optimal saving, you need to find what? Optimal saving rate. Do you see that? Optimal saving rate. So what is optimal saving rate? Okay, so let's do it just by trial and error. So you know this is production function. Is that right? You know that. And you know this. This is depreciation line. You know that? Depending on n plus delta. Okay, what is missing here? You remember? What I don't have here is S f of k. You know that? Why I don't have that? Because I don't know, and I want to find optimal saving rate. I don't know that yet. Okay? So that's why I cannot draw that now. Okay. So be careful. I am trying to find optimal saving rate. Okay? So I told you what I am going to do is just by trial and error. How trial and error? So your saving rate is little s. Saving rate is a number between 0 and 1. Yeah? Yeah, saving rate. Marginal propensity to save. 1 minus marginal propensity to consume. Is that right? So between 0 and 1. Okay. I pick a bunch of saving rates and try to find optimal saving rate by trial and error. Okay? So let me start by 0. Let me start by 0 and just gradually increase it to 1. suppose S equals 0. Is S equals 0, S equals 0, so then S f of k is what? S f of k is 0, is that right? Agree everyone? You see? By the way, do you see that? You got that the investment line is horizontal axis, S f of k, because S is 0. Okay? So, what is the statistical equilibrium here? Remember origin, last time we talked about that? Origin is statistical equilibrium. Very boring, we call that, because everything is 0. 0 output, 0 consumption, 0 everything. So here, by the way, one more thing before I go ahead, I have to tell you. When we say optimal investment to achieve what? So, right? I have to find, you know that each optimization needs an objective function. So you want to find optimal investment to maximize something, minimize something, is that right? Because you are working towards an objective. That is called objective function. See, in economics, generally, we want to maximize human welfare. And okay, in economics, we make life easier, okay? So we assume that the best representation of human welfare is consumption. Okay, so that's why number one target in economics is consumption. Whenever people talk about increasing human welfare at the end, it's more than that. But at the end of the road, it boils down, for example, to talk about, you remember micro utility max, but who can measure utility? So it boils down to consumption. So as you can see, I am choosing different saving rates to find maximum consumption per worker, everything per worker, okay? So don't forget that. Okay, so you see, maximum consumption would be 0. Let me choose, remember trial and error. Let me choose saving rate 20%. So then SF of KT would be what? SF of KT would be 20%, yes everyone? F of KT, is that right? So it would be something like this, 20 times F of KT. So this point is your statistical equilibrium. But remember I told you, remember that? I need that in a few minutes. That was for now. So this gap is representing consumption. The gap between production function and depreciation line. Can you see it here? So I put this here. So as you can see, initially, when saving rate is going up, consumption goes up. But does it go up forever? Let me choose half. So half would be what? Half would be half times F of K. So this is your statistical equilibrium. This is consumption. This is consumption per worker. Do you see that? So keeps going up. But does it go up forever? No. You can see here? For example, let me choose 80% saving rate. 80% saving rate. But look at that. 80% saving rate. You see, this is very close to production function. Is that right? So look at that. Saving rate is so little. As matter, the funny part is, if saving rate is 100%, so then what happens? You see here? Then what happens? SF of KT, when S is 1, would be production function. So as you can see, when saving rate is 1, production is maximum. But what is consumption? 0. So that's what, actually I have seen many people, many students make this mistake, and they think in economy we have to maximize output. No, bad idea. You see that? We maximize consumption. Consumption is representing welfare. For example, here, output is maximum, but people are dying because they don't consume, because they save it again. Do you see that? So be careful. That's why output is not an objective for humanity. Okay? So now if I connect, you see here I did my trial and error. Is that right? Trial and error. So as you can see, more investment is not a good idea necessarily. Yes, it's a good idea to some point that they're going to find it, but after that, more saving is not good, because more saving means what? Less consumption, after all. Is that right? Okay, so by the way, did you notice something here? I guess I went through that fast. You see here? You see? Okay, it's kind of a pink. You see this area, can you see that? I mean, here I can see that, but over there, pink is so faded. Okay, you see, this area is called consumption lens. Can you see it? It looks like a lens. So consumption is equal to vertical thickness. Vertical thickness of the lens is representing per worker consumption. Okay? So guys, I need to find. So you see, I want that. Is that right? This saving rate maximizes consumption. Okay, because here we have maximum consumption, maximum thickness of the lens. Okay, so this optimal saving rate, and optimal saving, and optimal investment. Okay, actually, I don't know why they named it like that. So this is called golden rule. Golden rule saving rate. Golden rule saving rate is optimal saving rate. Saving rate that maximizes consumption. Okay, worker consumption. So golden rule saving rate. And maximum consumption is called golden rule consumption per worker. Everything per labor, per worker. Is that right? So, see, here we just did it by trial and error and just by eyeballing. Is that right? But where is it? How can we find it? How can we find it? So, let's do graphical approach. You see, I want this. I want this SG. Okay? So, from graphical point of view, I want this statistical equilibrium, this point. Do you know what is special about that point, that statistical equilibrium? Point O? Anyone? So let me give you help. You see? Let's go anywhere to the left of SG. Okay? You see? Look at, you see here? And by the way, that is golden rule saving, total saving. You see? Anywhere to the left of point O, see, I drew tangent to production function. Now, you remember from microeconomics, tangent, the slope of tangent to production function is representing what? Anybody? Not micro, remember we did it in like chapter 3. So the tangent to production function is called what? Sorry? No. So when I have output versus input capital, okay, the tangent is your marginal product of capital. Marginal product of capital. Okay. How did we find marginal product of capital? We took derivative of production function with respect to capital. What is that? Graphically. When you take derivative, it means tangent. The slope of tangent. Is that right? So, okay, you see, anywhere to the left of point O, marginal product is this. tangent looks like this. Anywhere to the right of point O, tangent is like this. Does that help? How we can graphically find maximum consumption, maximum saving, and golden rule saving rate, which means point O. You see, to the left it's very steep. To the right it's very flat. So if I draw a tangent at point O, anyone? Is that right? Okay. You don't see it yet? So that tangent looks like what? Look at the graph carefully. Anyone? Who said that? Sorry. I don't get it. Exactly. So, or what you are saying here is that tangent is parallel to depreciation line. Because he says what? He says slope is n plus delta. This is what he said. So it means this, see what he observed. This is parallel to this. So parallel means what? The same slope. So it means marginal product, the slope of production function is equal to n plus delta, as he said. You see that? Parallel. Okay. So this is parallel. So this is exactly what he said. Slope of production function, marginal product of capital is equal to n plus delta. The slope of depreciation line. Because depreciation line and the tangent are parallel. Okay. By the way, this is just graphical. We are going to find it mathematically in a few minutes. Okay. Okay. So you see here. By the way, did you notice something? I quietly added one more thing. You see, at that point O, which is maximizing consumption, how much is capital? kg. You know that? Steady state equilibrium is kg. And output is yg. Golden rule output per worker, golden rule capital per worker, golden rule saving rate, golden rule consumption, okay, per worker. And by the way, some books show this by consumption maximum. The same thing, golden rule, okay, because we call other good. Okay. So you see it here? Marginal product, not at any point, at kg. You see, not this point, too flat, not this point, too steep, exactly at this point, when these two are parallel. So it happens at kg. It happens at kg. Can you see it here? But there is one problem with this equation. So this is optimality condition, for sure. Okay, no problem. But it has one problem. The problem is, you see, I want to find golden rule saving rate. Remember how much I have to save to be optimal. That doesn't, golden rule saving rate doesn't come from that equation, because that equation doesn't include SG. So you can find kg only. Is that right? Because only kg is unknown over there. N is fixed, delta is fixed, so you have production function, you can find kg. So you need one more thing, one extra equation to find SG. Where does that equation come from, guys? Can you help me with this? Okay. You see, generally this is enough. But this equation doesn't give you SG because it doesn't have SG. So you need one more piece of information to link kg to SG. So where does that equation come from? Can you guess? See? We are at point O. Point O is steady state equilibrium that maximizes our consumption, not any other possible steady state equilibrium points. Okay? That one. So point O is also, what did I say? Point O is steady state equilibrium. So a steady state equilibrium condition must hold. Remember, capital inflow must be equal to capital outflow. So I use that to find SG. Okay? So, you see, because point O not only maximizes consumption, after all, it is steady state equilibrium. Okay? So look at that. That is steady state equilibrium condition. Capital inflow is equal to capital outflow with one thing, kg. Okay? Steady state equilibrium when capital is kg. Okay, you see? So you find kg from here and plug it here, and you find what? SG. SG. Now, let me find this mathematically, the last one, which is completely convincing, and then we are going to do what? A numerical example. How we can calculate all these things. Okay? So mathematical approach. You see, we want to find maximum consumption. But remember I told you, remember I need that in a few minutes. Consumption at any point is vertical. Thickness of that lens. What is vertical thickness of that lens? So it's, you see, for example, let me give you a number. Yeah, you see here? So you see, at any point, this is consumption in general. Okay? Consumption is the gap between production function and depreciation line. So this gives me consumption. So I want this. So consumption is the gap between your vertical thickness, production function, minus depreciation line, the gap. But I want to choose K such that consumption is maximum, so-called kg. Okay? That's it. This is mathematical solution. You can maximize consumption directly. You don't need any graph, you don't need anything. Alright? Okay. So you know how to do this. We need to take derivative and set equal to 0. Okay? So take derivative of consumption function and set equal to 0. Derivative of consumption function set equal to 0. So this would be derivative of production function with respect to K. Derivative of this part with respect to K is n plus delta. Okay, but what is this? Marginal product of labor, marginal product of capital. And what is this? Slope of depreciation line. Look at that. This is the same condition that we found it just by eyeballing, looking at the graph. Yeah, the same condition. But how can I do this with numbers? Okay, let me go back to my favorite production function. You want my favorite production function? Okay, we have that. Now, remember, I changed it for you, I told you. Change it per capita everything. Population growth rate suppose is at 2%. Depreciation rate is 8%. What is golden rule saving rate in this economy? What is maximum consumption per worker? And kg, yg, everything. Okay, how can I do this? You remember, marginal product of capital must be equal to n plus delta. You know that? It cannot get easier than that. marginal product of production function, take derivative of this with respect to k, so it will be 0.6 kg to power of minus 0.07, just derivative. Yes? But be careful. I put kg here. Is that right? Because, you see here, these two are parallel only at kg, not anywhere else. Remember, to the right, flatter, to the left, steeper. So only at point kg, these two are equal. I mean these two. So marginal product of capital equal to n plus delta. Okay? So find kg. Kg it is. So how can you find kg? You need to have one of those calculators. You cannot do it manually. Okay, see, I told you, it gives you kg. It doesn't give you SG, golden rule saving rate. So, how can I relate and find SG? Steady state equilibrium. Point O is, after all, steady state equilibrium. So, remember, inflow of capital, S f of k, S is unknown, SG is supposed to be found. And what is this? Capital outflow. Capital outflow. Okay? So, okay, you can simplify it like this. Okay? But guys, look at here. See here, it's very interesting. See? Kg to power of minus 0.7 is 1 over 6. Agree everyone? Yes? Please focus. So it means this is how much? 1 over 6. Is that right? So SG times 1 over 6 is, okay, 5%. So multiply both sides by 6. Multiply both sides by 6. So this would be 1. SG is 5% times 6, which would be how much? 30%. 30%. So let me write it here nicely. So SG is 30%. So for this economy, golden rule saving rate, which is maximizing consumption, is 30%. Okay. Now, how much is SG? Sorry, I found SG. How much is kg? Okay, I told you you should have a calculator. Okay. So see here, what you do is you need to raise both sides to power of minus 1 over 0.7. Okay, so that gives you this number, kg. Okay, what is golden rule output, income per worker? Okay, that should be easy. So look at here, plug this here. So this gives you YG. YG. Now, I ask you just one question. How can I find CG, golden rule consumption per worker, which is supposed to be maximum? Yes? Anyone? Anyone? Is it easy? Yes?
Put kg into the SG and kg.
Yeah.
And then like the y, and then y is minus that.
Yeah, exactly. You see here, she's right. You see, we found golden rule saving rate. 1 minus that, so that would be golden rule, something like marginal probability consumed. So times income would be consumption. So 70%. Then SG is 0.3. So 1 minus 0.3, 70%, times YG would be golden rule consumption. So this consumption per worker is maximum in this economy. it here? So, yes, everyone? How did we get what?
How did you get
C?
Yeah.
Oh, okay. You see here? One more time. We got here. You remember we found optimal saving rate. So 0.3. But what is marginal profit consumed? 1 minus S. In this case, 1 minus SG. Is that right? So which would be 70%. So 70% times income would be consumption. Yeah, does it make sense? Is that right, everyone? Okay. Mr. Solo, he really deserved a Nobel Prize, honestly. By the way, today is just nothing. This is the first model. If you take a course in growth theory, this is first model out of 20. Okay, but first person after 100 years of silence about growth and optimal investment, okay? But still, he has to explain something. You remember? He has to explain himself. He discovered that economies are continuously growing. But his model doesn't show that, okay? So he came up with an idea. That is possibly another big contribution, okay? So, to explain that continuous growth. So, to explain that, let me do one exercise. Suppose I have point O, my economy is in very long run equilibrium, so-called steady state equilibrium. Is that right? Is that right, everyone? Okay. Suppose all of a sudden technology gets better. Okay? Something is discovered. Just actually, I wrote it one-time technological progress. Okay, so it means something, some big invention happens. Okay, what happens to my economy? Anyone? So graphical point of view, how did we show technological progress? We talked about that in chapter 3, and also you should have seen that 1 million times in micro class. Okay, so in this structure, if technology gets better, so what happens? Better technology means what? Means with same level of inputs, you can produce more output. Okay? It means what? It means this. Production function shifts up. Yes? Production function shifts up. But when production function shifts up, actually we call that FF. FF is better technology, superior technology than F. But look at that, it's not the only shift. Because here I have S F of K. So it means that shifts too. Is that right? Okay, when I put these two together, so where is my new steady state equilibrium? Remember? I find new steady state equilibrium by intersection of inflow of capital, outflow of capital. Okay, so if you go here, this is your new steady state equilibrium. Okay, let me draw it nicely. Can you see that? Can you see that? So better technology means what? Output, steady state equilibrium goes up from O to O prime. From O to O prime. So you see here, how? How does the economy go from O to O prime? You see here, so you see you have a jump, you have an initial jump, and then gradual adjustment. Gradual adjustment. A jump and gradual adjustment. Why jump? Because when you have this new technology with the same initial level of capital, right away can produce more output. Yeah, you know that? That is the definition of better technology. But after that, when you over here at this point, inflow of capital is more than outflow of capital. After that, capital is gradually adjusting towards O prime. So you have that your timeline. So you have a jump, and then a gradual adjustment to new steady state equilibrium. Okay, he talked about this. But you know, if technology can get better, it still has a problem. You see here, we went from O to O prime. At O, growth rate of economy was 0. You remember, for example, growth rate of output. You remember that? You see here, growth rate of output was 0. Eventually, growth rate of output becomes 0 again. You see that? So, output growth rate becomes positive temporarily. So even one technological progress cannot create continuous growth rate of economy forever. But you know, Mr. Solo came up with this idea. You know what he said? Can you imagine what? Do you know what he said? That revolutionized views to growth. So he said this is a one-time technological progress. Is that right? But don't forget that. Actually, don't forget, today we understand that better. I am talking about 70 years ago, okay, 80 years ago. He said technology is getting better and better every day. We don't have one-time technological progress. Technology is growing every day. So what does that mean? So it means next year, another shift. Next year, another shift. Next year, another shift. So by the way, another shift here, another shift here, another shift here. Is that right? So you are going to have what? See here? He said, steady state equilibrium continuously goes towards northeast. Is that right? Northeast. What does that mean, northeast? So it means when technological progress happens, northeast means output is higher, capital is higher. Both of them higher. Southeast means capital goes up, output goes down. Is impossible, all right? When production function shifts up, both of them go up. Please remember this southeast, northeast, okay? I come back to that next chapter. I need that, okay? This is how he solved the problem. He said, which changed everything, our view to growth was this. You remember I told you, people, especially old people like me, they always say engine of growth is investment. Not really. So what is engine of growth? This was a huge discovery. Technological progress is engine of growth. You understand here? Investment is good. Investment is good, but investment is helping you adjustment from O to O prime. Is that right? But after O prime, investment is not helping you anymore. You see that? So, to continuous growth, you need to have a new steady state equilibrium continuously. So that is how what we are thinking about. So if technology stops growing, our welfare stops getting better. I guess this is the best of his discovery. In fact, what he did was, so actually that links me to chapter 17, chapter 9. Chapter 9, let me start beginning of chapter 9. So there is my chapter 9. So in fact, In fact, chapter 9, I start from, because sometimes, you know, we finish chapter 8 one week, and we start chapter 9 next week, so I have here a reminder. So remember, continuous technological progress, shifts, curves, continues. But did you see that? This model has a problem. The problem is graphs are not stable. Graphs shifting forever. Graphs shifting forever. So, I mean, I cannot explain that to you. So what he did was, he created a new version of this model, that we talk about that next one, such that you have continuous technological progress, yet you don't have what? Yet you don't have shifts, okay? So how did he do that? Because here, he said this. He said, suppose production function, remember so far we said what? Production function is the function of capital and labor. Capital and labor. But he said, output is a function of capital but not labor. Effective labor. Effective labor. What is effective labor? You see? AL. Effective labor. So, effective labor, A is representing technology. So, A is representing technology is an index times L. Okay? For example, if A goes from 1 to 2, it means what? The same number of workers. The same number of workers can work like what? Twice more. So, for example, if you had 10 labor force initially, with twice better technology, the same 10 people can work like what? 20. Can you see that? Effective labor. Effective labor. So, labor force, 80, technology index. Actually, it's an index. You can imagine, index is one given year, and as technology gets better, you increase A. Okay? So, and by the way, the same properties, remember, constant return to scale, diminishing returns to capital, diminishing return to labor, everything like before. Anything like before. And then he assumed that labor force is growing at N% per year, and technology gets better G% per year. Just, he assumed that. He assumed that. So, G%, N% per year, G% per year. And remember, constant return to scale. He still assumes that we have constant return to scale. It means what? It means if you multiply all inputs by any number, except 0, output goes up by the same number, okay? So he chose this, lambda 1 over AL, 1 over AL, you see? All inputs are multiplied by 1 over AL, so output was multiplied by 1 y over AL. And then, you see, we have a new production function. This production function, you see, I am using hat, little k hat, little y hat. Little y hat is per effective worker output. Per effective worker output, little k per effective labor capital. Per effective labor capital. Is that? Now I have three things. Big Y, total GDP. Little y, GDP per capita. Y hat, GDP per effective labor. So little y, GDP per labor, Y hat, GDP per effective labor. Okay, let's take a 15 minutes break. And when you come back, you are going to complete his model and he solves his problem. So 10